We have Eran Malach, who's coming to us from Hebrew University, where he also works with Mobileye. He is a student with Shelov Schwartz and is working on a number of ideas related to theory of deep learning.
So thanks for having me here. So this talk will be about deep learning on the border between success and failure. Hopefully you'll understand what it means in a few slides. Deep learning is, as you probably know, very successful in practice. It's achieved great results on the ImageNet or in general image classification tasks. It's driving autonomous cars. Recently, there's great achievements in natural language processing, again, due to deep networks and deep learning. This is interesting. There's a toothbrush company. I heard about it recently. They embedded a deep network on the toothbrush. It helps you brush your teeth or something like that. This is another achievement of deep learning. Another interesting work is, of course, the CageNet. It's a network that makes everyone look like Nicolas Cage. I don't know if you can see in the images there. Another great milestone. On the theory side, on the other hand, we know, things don't look so bright. We know that the neural networks are, in general, computationally hard to train. Gradient descent or gradient-based algorithms can encounter bad local minima, and they could have bad generalizations, or the bounds for generalization that we have do not necessarily apply. So we have these two conflicting situations. Let's try to understand what's going on, and this is my perspective on it. Imagine the space of all distributions, and of course we have some success cases. So these are some distributions, I don't know, ImageNet or CFAR or images of Nicolas Cage, where deep learning greatly succeeds and advances technology. We also have cases where we have families of functions that we can show theoretically that deep networks or neural networks will succeed to learn. So linear data, this is the work we had. We showed, together with Alon Brutzkus and Amir Globozon from Tel Aviv University, we showed that the neural network can learn linear data when the data is linearly separable. So this is a family of function we can, a neural network succeed to learn. Another family of functions is functions come from the relevant kernel space. There's a lot of interest in neural tangent kernel, NTK. So these are another positive examples. And there's various other theoretical results showing other cases, other success cases of deep networks. On the other hand, we have distributions or family of distributions that we're not succeeding to learn. So these are kind of like the worst case examples, either that are computationally hard to train or that gradient descent fails to learn them. By the way, when I'm talking about deep learning in this talk, it will be learning neural networks with gradient descent. This is kind of like the scope. So, this is what people usually do. So for me, the holy grail of this field is kind of understanding where is the border between these two cases. Like, what distributions can we learn, what distributions can we cannot learn, and really have specific property or properties that separate these hard and easy distributions. And this, I think, is kind of a big open question. So some people may argue that most distributions in some sense are easy, or others would argue that most of them are hard, but we kind of want to understand where is the border. But this is a big question, so I will not attack it directly. What I will do in this talk is focus kind of like on the border area and try to look at borderline models. And what I mean by that is kind of like parametric families of distributions that are on the border. They have some success cases, they have some failure cases, and there's some property or knob that can turn you from success case to failure case and vice versa. right? So our ultimate goal is really to understand the space of all distributions, but this is hard, so we'll focus kind of like on the border area and find these examples of distributions where there's a single property or a few properties that make the problem easy or hard. Yeah, so this was some motivation. And I'll give a warm-up example, and we go through some more interesting things. Yeah, so the k-parity problem, this is a fairly standard problem. You're given a set of n input bits, plus or minus 1. There is an unknown subset of size k, where you should think of k as being rather small and n being rather large. And the target, the output of the function is just the product of these k bits. So if there's an even number of minus 1, the label will be 1. If there's an odd number of minus 1s, then the label will be minus 1. Right? This is the setting of the problem. Right? A very simple problem. You're given a set of bits, and there's only a few of them that actually matter, and the rest do not affect the function. So yeah, we can observe two instances of this problem. One where the x, the input, is drawn uniformly from a uniform distribution, where each coordinate is sampled with probability half plus or minus 1. The second instance is a slightly biased distribution, where the probability to see 1 is, say, 0.6, right? Not half and half, but 0.6. And I do a simple experiment. I train a one hidden layer, fully connected network. On these two instances, k here is small, it's 5, and n is large, it's 128. And what we see is very interesting. On the uniform case, we get a complete failure. It gets into random guess, nothing happens, the network doesn't train. On the biased case, on the other hand, it's an amazing success. We get to 100% accuracy, and the problem is solved, right? So these seem like two fairly similar cases, but we're seeing a very big difference in the behavior of the network. So this is kind of like a typical borderline case, right? Where you have both these very similar distributions, same target function, but very different behavior. Okay, so this is just an interesting example. Okay, we can go into a more generalized version of this instance. You get an input of, again, n bits, and here I will require that n would be a power of 2. The target function now is calculated by a tree-structured Boolean circuit. What I mean by that is we order the bits, and we put kind of like a tree on them. Each node in the tree is a Boolean function. Any arbitrary Boolean function, it doesn't be and or XOR, any Boolean function from plus minus 1, from 2 bits to 1 bit. And I guess it's fairly easy to see that this can implement the k-parity, so it's just a generalization of the k-parity problem, just slightly more interesting family of functions. And we want to train a neural network. This will not be a two-layer network, it'll be something more sophisticated. So what I do is I replace each gate by a mini neural network, what I will call a neural gate. It's trainable. It gets 2 bits. The hidden layer is ReLU activation. And the output layer, this I do for simplification, is the hard tanh. It's the piecewise linear of tanh. It's just clipping the ReLU, kind of. And again, for simplicity, I fix the weights of the second layer just to be randomly initialized plus or minus 1. So this is a neural gate, a very simple network, and you could observe that it can calculate any function. If you have enough nodes, it can calculate any Boolean function from 2 bits to 1. And to build the circuit, we just replace each gate with this neural gate, and we have a neural network of depth that is basically logarithmic in the size of the input. And we can train this whole thing to implement the circuit. So it's not a standard network, but I would argue that if this is the problem that you're facing, if you know that the target function comes from this tree-structured Boolean circuit, then it kind of makes sense to use this type of architecture. And what I'm going to analyze, it's not the standard end-to-end learning algorithm. I'm doing another simplification, and I'm studying a layer-wise learning algorithm. So what we do is we initialize the first layer randomly. Then we do an average pulling on the bits of the output of this first layer. So the first layer takes you from n bits to half n. And then we average pull, we get a single bit. And then this we will train against the label. So this is just gradient steps, just gradient descent with respect to the weight which is initialized. After we're done with that, we'll freeze this layer, initialize the next one, average pulling, train it, and then go on until we're done. This is not the fire alarm. You can all relax. Yeah, so this is a simpler algorithm. It's not so popular. Mostly people train the whole thing end to end. But there's work. There's a bunch of work that show that it's somewhat comparable to end-to-end training. There's a work that showed that even on the ImageNet data set you can get comparable results. So and it's easier to analyze. Yeah, so to give the theoretical results, I'll have introduce some distributional assumptions and some notations for that. So D will be some general distribution on plus minus 1 to the n. Gamma I is the output of the ith layer of the circuit. Remember, the target function that we're trying to learn is calculated by a circuit. So gamma I will be just the output of the ith layer of the circuit. Cij is the correlation or just the expectation of a product between an output of one node in the circuit and the label. So just the correlation from an output of a node to the label. And Iij would be just the influence, how much a single node influences the function. So we'll say it has no influence if the function ignores this node for all sets of input. Right. So the first assumption is that the distribution is a product distribution, meaning the input to each, the coordinates are basically independent from each other. We have a similar result for a slightly larger family of distribution, but this will be simpler to introduce. Another assumption, this is rather technical, is that the label, target label is not exactly biased. It's not exactly uniform. It's slightly biased toward positive or negative. And the third assumption is that for the input to each gate, either never appears or appears with probability epsilon. We have a similar result without this assumption. We get something a little bit weaker, but I'll introduce this just to give you the stronger results. So these are all, I would want to say, somewhat technical assumptions. The key assumption, or the property that I think is the most interesting here, is that there is some correlation between each influencing gate in the circuit to the target label, right? So we require that each gate, if it has influence, that the correlation to the label would be larger than the bias of the label. Of course, we cannot require it for gates that do not influence, but this is required only for the influencing gates. Right. So this is kind of like the main assumptions. And I guess you should be wondering what happens for the k-parity example, which is kind of like the motivation for all this work. So in the k-parity example, we look at the product distribution that is far away by chi from the uniform distribution. This is the thing that we require. And we see that in this case, we get that the correlation is large enough. It's polynomial in k, but k is, as we said, small. It's could be bounded by log n, and we get that we have sufficient correlation, right? So this is a fairly simple result, and which means that the assumptions that we just introduced hold for the biased case. All of them. I'm just showing the interesting one, but the others do. Right. So the main result here is we fix some distribution that satisfies all of our assumptions for any delta for a network that's big enough, but it's not very big. It's only logarithmic in the parameters. With high probability, when we're running the layer-wise optimization algorithm, we get a network that implements exactly the Boolean circuit or the target function that we're interested in. Everything is time and sample complexity polynomial in n, 1 over epsilon, 1 over delta, and 1 over beta, and log 1 over delta. So these are all the parameters. So this is good. So we can safely say that in the biased parity case, if k is bounded by log n, then the algorithm that we introduced converges in polynomial time, and this is fairly straightforward. Okay. Right. So what happens when the distribution is uniform? So of course, when the distribution is uniform, it's fairly easy to see that the correlation of every bit in the parity or in any parity would have zero correlation. So we cannot have our key assumption. And what happens is that the neural gate that is influencing but has zero correlation would just converge to a constant function, so it just eliminates its input, and therefore we cannot learn the parity, so the algorithm essentially fails. Right, so this is a conclusion. Well, we saw the experiment, but this is kind of like the theoretical intuition behind it. And it seems that local correlations is important. So this is kind of like this interesting knob that I was talking about. If you have correlations, if you're successful. If you don't have correlations, then you fail. This is really the borderline example. So just to give another motivation for this, I'm looking back at the real world images, and there we know that deep learning is successful. So what happens there? Do we have local correlations? So, well, it's not the same problem. It's hard to formulate it in the same way, but this is an interesting experiment. You take a neural network and train it on a single random 3x3 patch from ImageNet. Yeah, ImageNet is like the hardest task we can come up with. So this is, should be really hard. And maybe the battery is. In any case, the result that we have is 2.6 top 5 accuracy, which is not great. Yeah, it's not too good, but the random guess, you have to guess 1 out of 5 categories out of 1,000 would be 0.5%. So this kind of hints that you have some correlations even if the patch is very, very small. So it's not really a great analogy to the circuits example, but it kind of hints that this might hold true for natural data as well. Okay, so we saw these two examples, the K-parity and the Boolean circuit that is a generalization of this space of functions. And now we move on to another example, and this would be fairly different than the ones that we already introduced, but I will try to find another property that kind of differentiates between success and failure. Right, so before we do that, this is an interesting question that many people are interested in. Which distributions or what kind of problems deeper networks are much better than shallow ones? So we know from our practical experiments that deeper is in a sense better. The deeper you take the network, the more successful you are. So the question arises, can we give called justifications for that. And there are several results on this matter. And usually what they say is there are families of functions or distributions that can be expressed by a small, in terms of parameter, deep network. But to express it with the wide, shallow network, you have to get an exponential number of parameters. Right. So we'll introduce another distribution like that, and we'll try to look at it from a different angle. So first, let's talk about fractals. These are interesting mathematical objects. And I'm going to look at a specific families of fractals. These are ones generated by iterated function systems. So what we do is start with some initial set, say a cube in an n-dimensional space. We apply a set of R affine transformations on this cube. So you can see we apply it once, and then we take the whole thing and the same transformation, apply them again, and get a more complex structure. So we do this thing again and again, and we get more and more complex structures. And I would call each step here the level of the set, or the level of the fractal. And we'll do these steps of this process, and the depth, so-called, of the fractal set will be d. Right? So this is just a mathematical procedure. And the reason I'm introducing it is to generate distribution for a binary classification task. So the distribution that I'm looking at is a very simple one. I take all the negative examples to be outside the set that I generated, and all the positive examples would be inside the set, right? So this is just a definition for a target function, and the underlying distribution could be whatever. I'm not requiring anything at this point. So this is just a way to generate these kind of like complex and maybe interesting distributions that we'll try to look at deep networks, how they do on. Right, so this is a depth separation result. Consider a fractal generated by R functions and up to depth d. Then any distribution that you can think of that implements this fractal can be, there exists a network of depth that is, say, linear in D and width is linear in N and R, which is the dimension and the number of affine transformation, which realizes this distribution exactly. Yeah, so the proof for this is rather straightforward. We can always implement the first cube with a neural network. And given that we already, and this would be the first set that we start with, and given that we implemented the d-1, the last set, every point in the d set would have an origin in the d-1 set, and we can implement this inversion of the affine transformation to move everything back to the d-1 set, and then we can apply the first neural network. So this is nice because it kind of like deep networks play nicely with these fractal sets. This is some a nice result. And to give from the other hand, if we want to implement these distributions with a shallow network, or network is not too deep, then we have to have a width that would be, in a sense, exponential in the depth of the fractal, right? So, and this is just counting linear regions. It's not very sophisticated. Right, so this is really the depth separation. So a deep network, we can implement easily the distributions, and for a shallow network, we have to have exponential dependence on the depth of the fractal. Yeah, so this is what we saw, but we're interested not only in expressing it exactly, we were interested in also how well we can approximate it. And to analyze the approximation, what I'm going to do is I'm going to look at what I call the approximation curve, is how much of the distribution is concentrated on what levels of the fractal set, or in other sense, what is the loss that you encounter when you just take the indicator of a higher or a lower set in this process, right? If I just take, I cannot implement the whole structure exactly, but I'm trying to implement something that is more simple. What is the loss that I encounter? So this will be the approximation curve, and these are just two examples. So one is like a nice curve that each level has its own weight, and not everything is weighted on the last kind of hard levels of the fractal. And the other one is the one where everything is concentrated in the hard part. So you can see that the first should be easy and the second should be hard. And what we get here is that this approximation curve that tells us how much weight we put on each level really determines how well a shallow neural network is going to approximate this whole function. So remember, a deep neural network of depth d would give us 0 loss, but a shallow neural network would give us something that is really measured by this approximation curve. So it's really just can approximate a lower level in the fractal set. So if we take this approximation curve and put all the weight on the fine details, or put everything is like shallow, you get really a very bad error if you try to take a lower level, and then all the weight is on the fine details, then this means that a shallow neural network would be very similar to a random guess, right? You're going to be only very slightly better than a random guess. And this is, I will call a strong depth separation, right? We have depth separation where a deep network gets 0 loss, and a shallow network gets really a random guess. So this is really a big gap. So what happens, but this is just the approximation. This is not, has nothing to do with learning yet. What happens when we try to run gradient descent? So I'll analyze a very simplistic form of this problem. Interested only in the Cantor set, which is a one-dimensional creature that's just, we split the line in each iteration, so we get these more and more complex one-dimensional things. And the result that we get here is this this is when we're trying to learn a network with gradient descent, and it's initialized in kind of like a standard way. We take this fractal distribution on the Cantor set and initialize some network. It could be deep or shallow, and as long as the logarithmic, the log of the number of parameters is not bigger than the depth of the fractal, what we get is that on initialization, the gradient is governed by the approximation curve, right? So if the curve is very flat and it's very close to a random guess up until the end, up until you find details of the fractal, what we're going to get is that gradient descent will be essentially, the gradient will essentially be 0. Right, and this implies that if we're in this strong depth separation case, right, when we have a very big gap between a deep network and a shallow network, in this case, gradient descent will essentially fail, right? Yeah, so this is another interesting property, because we wouldn't have known this if we were just analyzing the expressivity or the approximation error of the neural network. But once we try to think about gradient descent and the optimization process, then we find out that the strong depth separation really makes gradient descent fail. So what happens when the depth separation is not so strong? We kind of have like a gradual approximation with shallower neural networks. In this case, we can see that when the approximation curve is kind of nice, we get up to 100% accuracy, and the harder it is to approximate the distribution with a shallow network, the harder it is to learn it with even a deep network. This graph is, I'm showing here the accuracy for training a deep network on various distributions that are parameterized by this approximation curve. Yeah, so just again, to do a slight comparison to what we see in natural data sets. So this is the graph on the left is the contour, a two-dimensional version of the contour distribution, where we have 5 levels of this fractal, and we try to train different networks. So the colors you see are the depth of the network. So the red one will be 1 hidden layer, the blue one will be 2 hidden layer, et cetera, et cetera. And what you can see on the left is that you have this kind of like gradual improvement when you increase the depth. So it's not that the shallow network gets really just a random guess performance. It gets up to, I don't know, 70% or 75%. And the more you increase the depth, the more you improve the function. So you do gain from depth, but you cannot gain the whole way. It's not that shallow is like random guess and deep is gets 100%. Just to compare this to what happens on natural data set, this is the CFAR data. We do a very similar experiment, train networks of various depth and width. Again, we see this, and this is, here you have to guess 1 out of 10 categories. So the shallow network gets above 70%, and this is well above chance level. And the more you increase the depth, the more you gain from this, from having more depth to your network, but you don't gain the whole thing. It's not that you start from random guess and get to I don't know, 86% or whatever it is. This is the right one is CNNs, right? It's convolutional networks, just kind of like the standard thing to train on CFAR. And you can, I don't have it here, but you can see a similar behavior on ImageNet, where 1 hidden layer already gets you to 25%, which is, again, above chance. Right, so this is kind of like the image that I was trying to draw. We have all these success cases and failure cases, and we mostly focus on these 2 extremes, and I was trying to aim for the border, trying to understand the families of distribution that kind of like lie on the border and are sometimes we can learn them, sometimes we cannot, and try to understand what the properties are. Yeah, so just to summarize, we know that learning deep networks is computationally hard, but it works in practice. As we showed, you can brush your teeth with that. Current theory studies either success cases or failure cases. And we're trying to study this border, the borderline cases where a simple property can make you succeed or fail. So in the K-parity, we're comparing uniform and biased distributions. For Boolean circuit, we talked about local correlations, which made the algorithm succeed. And in fractal distributions, we showed that the strong depth separation that is very appealing from an approximation point of view really makes the network fail. Yeah, so of course, future questions would be, are there other interesting borderline models, any other important properties, and really trying to kind of like figure out how this space of distribution looks like. Okay. Any questions?
Hi, just wanted some clarification. So the assumption about correlations is for every level of the tree?
Yes. It's about every gate in the circuit that is influencing the function, right?
And the neural net that's learning is has a little neural net at every gate?
Right.
That structure?
Yeah.
Okay.
Yeah, coming back to the local correlations and the 3x3 pieces of the images for ImageNet, I wonder if you tried an adversarial version of this. You might be able to modify the images in a way that you wouldn't detect as a human, but to kill those correlations, and then can you train it?
Yeah, it's a good question. I haven't tried it. I think there's some works that did something similar, but Okay, this is like one point is I'm not claiming that local correlation is everything there is. Maybe you can kill the local correlation, but the network will still learn. Maybe there are other properties, but it's certainly an interesting one that you can see in even natural data sets.
Can you comment, though, on the sort of relation with the classic idea that when you train a perceptron, you should have whitened inputs?
You have widened
Gradient descent will be faster when you have
Right.
whitened inputs. So just, is there any relation to these two situations?
I guess what you're trying to say that in a parity, we like this uniform distribution hurts us, but in the perceptron, it in a sense helps us. In any case, the uniform versus biased in a parity case is just an example of two distributions that are one is bad and the other one is good. But it doesn't have to be that, like for other functions, there could be another bad distribution and other good distributions, right? So it's not that the uniform is bad for everything. We know that in some cases, uniform is good, and it's even better than other distributions. So it's just a property of the parity example, but it shows you that there could be good and bad distributions that look, in a sense, very similar.
You seem to assume that there is a nice border between easy cases and hard cases. Is it possible that there is no interior in either of these domains? That is, for every hard problem, you can tweak it a little bit and it becomes easy, or for every tractable problem, you can tweak it a little bit and it becomes intractable.
So, this is an illustration. I'm not like you can. I'm not saying that if you I don't know project the distributions to two-dimensional space, this is what you'll see. So yeah, of course, it's more complicated than that, and there might be kind of like entangled or very not like a strict border between them. But we do want to come up with properties, at least, that separate these cases. So I don't know, maybe your properties, is it learnable or not? So maybe.
So I have a question about this local correlation. Is this, did you try to get to kind of, by increasing correlation, becomes again hard? So between basically going from things that are not trainable to become, easy, hard, easy.
So in a sense, the parity example is this, right? We remove the correlations by moving to the uniform distribution, and then we see that it fails. So are you talking about natural data sets?
Yeah.
So for natural data sets, we didn't, we didn't try it, but it sounds very interesting. Again, I'm not claiming that this is only property. So maybe you can erase it. Maybe you can construct a data set where there's no local correlation, but still you're successful. Maybe there's other properties. But I'm just pointing to a very interesting one that seems to appear in like a natural set.
Okay, thanks.
So I don't know if this is a question or comment, but in general, in computer science, we know that problems can get easy or hard by changing very small things. So this is not special to learning. Definitely not to deep learning. I mean, you can take a graph theoretical problem, change just one little thing in distribution, it becomes easy or hard. So this is a failure in some sense of the paradigm of theoretical computer science, which is not, it's simply too crude to really tell us the difference. And I'm just putting it as a question, I mean, whether this type of theory, I mean, that focus on the worst case analysis and on the, try to make clear separations where we can't make it in any other branch of theoretical computer science, is this the right way to think about deep learning?
So it's a good comment and it's a good question. I don't know. Like, of course, in other problems, other algorithmical problems or other problems in computer science, you see these effects. But here we're interested in a very specific algorithm that happens to interest. We're interested in various aspects of it. So I really think that the big question, as I stated it earlier, is to find, a complete specification of this distribution space, right? When does it succeed? When does it fail, right? This is the ultimate goal. So this does not achieve this goal, but maybe it's a step to, if we want to uncover properties that are important, and this, it might be important for a practitioner, that they want to know if the data set that they're constructing is going to work or not. Right, so if we want to uncover properties, I'm claiming that this might be a way to go. Maybe no. Maybe you're just finding, very simple properties, but identifying the whole space is much, much more complex, and we're not going to get.
Okay, so let's thank our speaker one more time.